Jupiter is not a planet the way Earth is a planet. When you think of a planet, you probably think of something solid, something you could stand on. Jupiter is nothing like that. It is a colossal ball of gas and liquid, mostly hydrogen and helium, with no definable surface whatsoever. If you try to land a spacecraft on Jupiter, you would simply sink. You would fall through layer after layer of increasingly dense atmosphere, the pressure crushing you like a tin can, the temperature rising around you until you dissolved into the planet itself. There is no ground. There is no bottom in any meaningful sense. What there is, however, is a storm that has been raging for at least 350 years. We call it the Great Red Spot, and it is a storm larger than the entire Earth, a hurricane so ancient and so powerful that no one alive today, no one who has ever lived, has seen it begin or seen it end. It just keeps going, spinning in endless fury, as if Jupiter itself is trying to show us just how small and temporary everything we know really is. The sheer scale of Jupiter rewires your brain if you let it. Jupiter's diameter is about 11 times wider than Earth's. Its mass is more than 300 times greater than our planet's. It has at least 95 known moons, some of which are among the most fascinating and potentially habitable worlds in the entire solar system. One of those moons, called Europa, is covered in a thick shell of ice, and beneath that ice, scientists believe there is a liquid water ocean that has been sitting there for billions of years, warmed by gravitational forces pulling the moon back and forth in its orbit. That ocean may be twice the size of all of Earth's oceans combined, and where there is liquid water, there is the possibility of life. Not little green men, not aliens with spaceships, but microbes, single-celled organisms, the kind of life that first appeared on our own planet billions of years ago and eventually evolved into everything alive today, including you. The idea that something might be swimming in the dark waters beneath Europa's frozen surface, completely unaware that the universe even exists beyond their ocean, is one of the most breathtaking possibilities in all of science. But to really understand why Jupiter matters, why this giant planet is more than just a pretty light in the sky, you have to understand what Jupiter does for Earth. Jupiter is, in many ways, our guardian. Because of its enormous gravitational pull, it acts like a cosmic vacuum cleaner, attracting and absorbing asteroids and comets that might otherwise be aimed straight at us. Scientists believe that early in the solar system's history, Jupiter was responsible for deflecting or absorbing countless objects that could have disrupted the development of life on Earth. Without Jupiter, our planet might have been bombarded far more frequently by large impacts, and the complex life that eventually evolved here might never have gotten the chance. The very existence of you, of every human being who has ever lived, of every animal and plant and microbe on this planet, may in some way be connected to a giant ball of gas sitting 484 million miles away. That is the kind of connection that should stop you in your tracks. That is the kind of relationship between objects in space that reminds you the universe is not a collection of random, unrelated things. It is a web, intricate and interconnected in ways we are only beginning to understand. Now, to truly appreciate what is out there, we need to travel back, not a few centuries, not a few thousand years, but all the way back to the very beginning. Approximately 13.8 billion years ago, everything that exists, every atom in your body, every star in the sky, every galaxy racing away from us at incomprehensible speeds, was compressed into a single point, smaller than anything you can possibly imagine. Not small like a grain of sand, not small like an atom, smaller than that. Incomprehensibly, impossibly small. And then, in an instant that physicists call the Big Bang, everything exploded outward. But calling it an explosion almost misses the point. It was not an explosion in the way we normally think of explosions, where something blows up and the pieces fly outward through empty space. The Big Bang was the creation of space itself. Before it happened, there was no space, there was no time, there was nothing, and then, suddenly, there was everything. Trying to imagine what existed before the Big Bang is like trying to imagine what is north of the North Pole. The question itself may not be answerable because the concepts we use to ask it, before, outside, around, may simply not apply to a reality without space or time. In the first fraction of a second after the Big Bang, the universe was a place of almost unimaginable violence and energy. Temperatures were so extreme that even the particles we think of as fundamental, the protons and neutrons and electrons that make up atoms, could not yet exist in a stable form. The universe was a seething, boiling plasma of raw energy, too hot and too dense for anything we would recognize. But as it expanded, it cooled. And as it cooled, particles began to form. And from those particles, atoms assembled themselves, mostly hydrogen and helium, the two simplest elements in nature. For hundreds of millions of years, the universe was dark. There were no stars, no light, just vast clouds of hydrogen gas drifting slowly through the expanding emptiness. Then gravity, that most patient and persistent of forces, began to pull those clouds together. And as the clouds collapsed under their own weight, the pressure at their cores became so intense, so enormous, that hydrogen atoms began fusing together, releasing energy. Stars were born, the universe lit up, and the era of darkness was over. The birth of the first stars marked one of the most consequential moments in the history of the cosmos. Those first stars were not like our sun. They were enormous, many of them hundreds of times more massive, burning with ferocious intensity, blazing through their fuel at rates that would have made our sun look like a flickering candle. And when those massive stars exhausted their fuel, they did not go quietly. They exploded in what we call supernovae, catastrophic detonations so powerful that for a brief moment, a single exploding star can outshine an entire galaxy of hundreds of billions of ordinary stars. But those explosions were not merely destructive, they were creative. In the furnace of a dying star, heavier elements are forged: carbon, oxygen, nitrogen, iron, gold, everything on the periodic table beyond the simplest atoms. When the star exploded, it scattered those elements across space, and over billions of years, those elements drifted together, caught in the gravity of new stars forming, and eventually became the planets, the moons, the asteroids, and eventually, impossibly, the living things that populate at least one small world, orbiting one ordinary star in one unremarkable corner of a vast spiral galaxy. You are, quite literally, made of stardust. The iron in your blood was forged in the death of a star billions of years ago. The calcium in your bones came from the same process. You are not just looking at the universe, you are a part of it, assembled from its ancient debris, briefly alive, briefly conscious, briefly capable of wondering where you came from. Our galaxy, the Milky Way, is the stage on which all of human history has played out. From our tiny vantage point, we can look up on a clear, dark night and see its faint band of light stretching across the sky. The combined glow of 200 billion stars seen edge on from our position within the disk. The Milky Way is about 100,000 light years across, which means that light, traveling at nearly 300,000 kilometers per second, takes 100,000 years to cross from one side to the other. Our solar system sits about 27,000 light years from the center, orbiting the galaxy's core about once every 225 million years. That means the last time Earth was in the position in the galaxy that it currently occupies, the most complex life on our planet was early dinosaurs. The time before that, multicellular life was just beginning. In cosmic terms, the entirety of human civilization, every war, every empire, every invention, every great work of art and science and music has taken place in less than the blink of an eye compared to the age and scale of the galaxy we call home. At the center of the Milky Way, something extraordinary lurks. Something we once thought was purely theoretical, something so extreme and so strange that even the greatest minds in physics spent decades debating whether it could actually exist. At the center of our galaxy, about 27,000 light years away, there is a supermassive black hole. Its name is Sagittarius A star, and it contains the mass of about 4 million of our suns, compressed into a region of space that is, in cosmic terms, surprisingly small, roughly the size of the distance from the sun to Mercury. A black hole is one of the most dramatic objects in the universe, and it is also one of the most misunderstood. A black hole is not a hole in space. It is not a void or an emptiness. It is, in fact, the opposite of empty. It is a region of space where matter has been packed so densely that its gravity becomes so overwhelming that nothing, not gas, not dust, not particles, not even light, can escape. Once you cross the boundary of a black hole, called the event horizon, you are inside a one-way door. You can never come back. The universe you knew ceases to exist in any meaningful way. The strangeness of black holes goes far beyond their ability to trap light. Black holes do things to space and time that feel almost like science fiction, but are actually well-supported science. As you approach a black hole, time itself begins to slow down relative to the outside universe. This is not a metaphor. This is not a poetic way of describing how terrifying it would be. This is a real, measurable, experimentally verified consequence of Einstein's theory of general relativity, which tells us that massive objects warp the fabric of space-time around them, and the more massive the object, the more extreme the warping. Near a black hole's event horizon, the distortion of time becomes so severe that a person hovering just outside it would age only 1 second for every very long span of time experienced by someone far away. If you could somehow survive the journey and hover near the event horizon of a large black hole for what felt to you like a single hour, you might return to Earth to find that thousands of years had passed. The universe would have moved on without you. Everyone you knew would be long dead. Civilizations would have risen and fallen, and you would step back into a world that was no longer yours, bewildered by a cosmos that aged around you while you stood still. The concept of time dilation is one of the most profound and unsettling ideas in all of physics, not just because it is strange, but because it is true. We do not just theorize that time passes at different rates depending on gravity and velocity. We measure it. The GPS satellites orbiting Earth have to account for time dilation every single day because time passes slightly faster for them than it does on the ground, thanks to the difference in gravitational field strength. Without corrections for time dilation, GPS systems would drift by kilometers every single day. Your phone uses general relativity to tell you where you are. Einstein did not just explain a philosophical curiosity about time. He rewrote the rules of reality in a way that turned out to be both deeply true and practically useful. And if time dilation is real at the gentle level of Earth's gravity and orbital speeds, imagine what it must be like near the edge of a black hole, where gravity is 1 billion trillion times more intense. Time there is not just slower. Time there is almost stopped. From the outside looking in, matter falling into a black hole appears to freeze at the event horizon, stretched and distorted by the extreme curvature of space-time, forever suspended in the moment of crossing over, as if the universe itself is refusing to let go. Beyond our galaxy, the universe stretches out in ways that strain every human intuition about size and scale. The Andromeda Galaxy, our nearest large galactic neighbor, is approximately 2.5 million light-years away. That means when you look at it in the night sky, and you can see it with the naked eye on a clear, dark night, a faint smudge just barely visible, you are not seeing Andromeda as it is now. You are seeing it as it was 2.5 million years ago. The light that reaches your eyes tonight left that galaxy when our ancestors were barely recognizable as human, when Homo sapiens had not yet evolved, when the world looked almost nothing like it does today. Everything you see in the night sky is the past. Some of the stars you see no longer exist. They burned out thousands or millions of years ago, and their light is still traveling toward us, a ghost image of something that is already gone. You can stand in your backyard and look up and see the universe as it was at 100 different times in history, all simultaneously, all mixed together in the same field of view. Andromeda is heading toward us, not quickly for human standards, but inexorably, inevitable over cosmic time. In about 4.5 billion years, Andromeda and the Milky Way will collide. The collision will not like two cars crashing. The distances between individual stars in both galaxies are so enormous that the vast majority of stars will pass right by each other without hitting anything. But gravity will reshape both galaxies entirely. The gas clouds will smash together, triggering massive waves of new star formation. The central black holes of both galaxies will spiral toward each other and eventually merge into one colossal, supermassive black hole. What emerges from the collision will not be two spiral galaxies anymore. Over billions of years, the gravitational chaos will settle into something new, a giant elliptical galaxy, a massive, roughly oval cloud of stars with no spiral arms, no coherent rotation, just a slow, majestic drift of hundreds of billions of stars in a new arrangement. Astronomers have already given this future galaxy a name. They call it Milkomeda. And somewhere within it, billions of years from now, our descendants, if they still exist in any form, might look out from whatever world they call home and see a sky so different from ours that it would be unrecognizable. The deeper you go into the universe, the stranger it becomes. Beyond our local group of galaxies, beyond the clusters and superclusters of thousands of galaxies bound together by gravity, lies the large-scale structure of the universe. And it is unlike anything most people have ever imagined. When astronomers map the positions of galaxies across billions of light years, what they find is not a random scattering of points. What they find looks like a vast cosmic web. Galaxies cluster together in long filaments, like threads in a three-dimensional spiderweb. And at the intersections of those filaments, giant clusters of thousands of galaxies pile up in enormous concentrations of matter. Between the filaments are vast voids, regions of space hundreds of millions of light years across that are almost completely empty, containing very few galaxies at all. This structure, this web of filaments and voids, is one of the most remarkable things in existence. It is the largest structure in the observable universe. And it was not designed or planned. It emerged naturally from the physics of the Big Bang, from tiny quantum fluctuations in the early universe that got amplified over billions of years by gravity into the cosmic web we see today. And yet, here is where things get truly mysterious, truly humbling. All the matter we can see, all the stars, all the galaxies, all the planets, all the gas clouds, everything that emits or reflects or absorbs light makes up only about 5% of the total content of the universe. 5%. The other 95% is something we cannot see, cannot touch, cannot detect directly with any instrument we currently possess. About 27% of the universe is made of something called dark matter. We know it exists because we can see its gravitational effects. Galaxies spin in ways that should be impossible if they only contained the visible matter we can see. The outer edges of galaxies spin just as fast as the inner regions, which should not happen by normal physics unless there is a large amount of invisible matter distributed throughout and around each galaxy, providing additional gravity. That invisible matter is dark matter, and despite decades of searching, we have absolutely no idea what it's made of. It does not interact with light. It does not interact with regular matter in any way we can currently detect. It just sits there, everywhere, invisible and mysterious, holding the universe's structure together with its gravity, making the cosmic web possible, making galaxies themselves possible, and remaining completely unknown to us. The remaining 68% of the universe is even stranger. It is something called dark energy, and it is responsible for one of the most unsettling discoveries in the history of science. In 1998, two separate teams of astronomers were studying distant supernovae, exploding stars so bright they can be seen across billions of light years, to measure the expansion rate of the universe. They expected to find that gravity was slowing the expansion down, the way friction slows a ball rolling across the floor. Instead, they found the opposite. The expansion of the universe is not slowing down. It is speeding up. Every galaxy beyond a certain distance is accelerating away from us, moving faster and faster as time goes on, driven by some mysterious energy embedded in the fabric of space itself. This force, this dark energy, is not just passively present, it is winning. Over billions of years, it will drive galaxies so far apart that the night sky will eventually go dark. Galaxies will move beyond the observable horizon, their light unable to ever reach us again. In the far, far future, a civilization in this universe will look up at a night sky and see nothing but darkness, because all the other galaxies will have been carried away by the relentless expansion of space. The universe, on its largest scales, is not just mysterious, it is actively hiding its own history from its future inhabitants. Given all of this, the vast scale, the billions of galaxies, the hundreds of billions of stars in each, the planets likely orbiting most of those stars, how could we possibly be alone? This is the question that haunts modern science, that keeps astronomers up at night, that has driven one of the most ambitious searches in human history. The Fermi paradox, named after the physicist Enrico Fermi, who famously asked the question over lunch one afternoon, puts the dilemma in stark terms. If intelligent life is likely to exist elsewhere in the universe, given how common stars and planets are, and how life seemed to arise on Earth relatively quickly after conditions allowed it, then where is everybody? Why have we not heard any signals? Why have we not been visited? Why is the universe so hauntingly silent? There are many proposed answers to this paradox, and some of them are more disturbing than the question itself. Maybe intelligent life is extraordinarily rare, and we are one of the only civilizations, perhaps even the very first, to reach the level of technology needed to ask the question. Maybe civilizations tend to destroy themselves before they reach the point of interstellar communication. Maybe there are signals all around us, but we are not yet sophisticated enough to recognize them as signals. Or maybe, most unsettling of all, there is something out there, some pattern, some law of nature we have not discovered yet that consistently prevents civilizations from advancing to the point of making contact. The search for extraterrestrial life has taken many forms, from the radio telescope searches of SETI, the search for extraterrestrial intelligence, to the direct exploration of our own solar system's most promising locations. NASA's missions to Mars have found evidence of ancient riverbeds, of minerals that only form in the presence of water, of chemistry that suggests Mars was once a warm, wet world that might have supported microbial life billions of years ago. The Mars rovers have found organic molecules in ancient rock, and the planet's atmosphere shows occasional methane spikes that remain unexplained. On Earth, methane in the atmosphere is almost entirely biological in origin. The same might not be true on Mars, but the possibility lingers. Meanwhile, the missions to the icy moons of Jupiter and Saturn, Europa, Enceladus, Titan, have revealed ocean worlds that may be among the most likely places in the solar system to find living organisms. Enceladus, a small moon of Saturn, is actually venting water vapor and organic compounds from cracks in its icy surface into space. A spacecraft flying through that plume could, in theory, sample the ocean beneath without ever landing on the moon itself. We may be, right now, within a generation or two of finding definitive evidence that life exists or has existed beyond the Earth. And if we find it, even in the form of a single bacterium frozen in Martian rock, it will be the most important discovery in the history of our species, because it will mean that life is not a miracle that happened once by cosmic accident. It will mean that life is something the universe does. It will mean that in a cosmos of trillions of worlds, life, in some form, is everywhere. Let us talk about what it would mean to travel to some of these places. When you watch science fiction, spaceships zip between planets and stars in hours, maybe days. In reality, the distances involved are so enormous that they present one of the most fundamental engineering challenges our species has ever faced. The fastest spacecraft humanity has ever built, the Voyager 1 probe, launched in 1977, is currently about 24 billion kilometers from Earth. That sounds impressive until you realize that the nearest star to our Sun, Proxima Centauri, is approximately 40 trillion kilometers away. At Voyager's current speed, it would take about 73,000 years to reach Proxima Centauri. If we want to visit other stars in anything resembling a reasonable human lifetime, we need to fundamentally rethink how we travel. And here is where physics offers us an extraordinary, if terrifying, gift. Because of time dilation, a ship traveling at a significant fraction of the speed of light would experience time passing much slower than stationary observers. A spacecraft traveling at 99% of the speed of light would experience time passing about 7 times more slowly than on Earth. A spacecraft at 99.99% of the speed of light would experience roughly 100 times less time. In theory, an astronaut on an extremely fast spacecraft could travel to a star 20 light-years away and experience only a year or two of travel time, arriving while barely having aged, even though 20 years have passed on Earth. Time dilation is not just a theoretical curiosity, it's a genuine mechanism written into the laws of physics that could one day make human travel to the stars possible, at least for the traveler, even if everyone they left behind ages and dies while they are gone. The question of humanity's future in space is not just a scientific question, it is a deeply human one, connected to who we are, what we value, and what kind of story we want our species to tell. Right now, we are in the early, fragile dawn of becoming a spacefaring civilization. We have been to the moon, we have robots on Mars, we have spacecraft orbiting Jupiter, orbiting Saturn, studying the sun, peering back at the edge of the observable universe with instruments of breathtaking precision. In 2021, the James Webb Space Telescope launched and began revealing the universe in levels of detail that previous generations of astronomers could only dream about. Webb can look so far into space, which also means so far back in time, that it has captured images of galaxies that formed just a few 100 million years after the Big Bang, when the universe itself was still young and wild and just beginning to take shape. The images Webb has returned are not just scientifically valuable, they are works of art. They show galaxies in the process of forming, collisions between ancient star systems, delicate pillars of gas and dust where new stars are being born, the raw material of future worlds hanging in the dark between the light. Looking at them is looking at the universe remembering what it used to be. The path forward for humanity in space involves challenges that will define the next century of our civilization. We need to learn how to live in space for extended periods, which means solving profound problems of radiation exposure, bone density loss, muscle atrophy, psychological isolation, and supply chain management across vast distances. We need to develop propulsion systems that can move humans fast enough to make interplanetary travel practical, and eventually to push toward interstellar distances. We need to think carefully about planetary protection, how we ensure that we do not contaminate other worlds with Earth life before we can determine whether those worlds already harbor their own life. And we need to grapple with the deeper ethical questions that space exploration raises. If we find microbial life on Mars, do we have the right to send humans there and potentially wipe out a biosphere that evolved independently over billions of years? If we encounter intelligent life elsewhere, even just a radio signal, how do we respond? Who speaks for humanity? Who decides? These are not hypothetical questions for distant generations. They are real questions that real people working right now in space agencies and research institutes and policy meetings are beginning to take seriously, because the pace of discovery is accelerating and the universe is not waiting for us to be ready. There is a theory in physics and philosophy that occasionally surfaces in discussions about space, time, and the nature of reality, and it is one of the most mind-bending ideas you will ever encounter. It is called the simulation hypothesis, and while it is not mainstream science, it is taken seriously enough by enough serious thinkers that it deserves attention. The idea is this. As civilizations advance, they develop the ability to run incredibly detailed computer simulations. Eventually, a sufficiently advanced civilization might run simulations of entire universes, complete with stars, planets, galaxies, and perhaps even conscious beings who experience those simulated universes as real. If that is possible, then the number of simulated universes could vastly outnumber the one physical universe, and statistically, any given conscious being is more likely to be living in a simulation than in the base reality. The physicist Nick Bostrom formalized this argument, and while proving or disproving it may be fundamentally impossible, the fact that it cannot be easily dismissed is itself remarkable. We live in a universe where the laws of physics are described by beautiful, precise mathematics, where the fundamental constants of nature seem fine-tuned to allow complexity and life to exist, where consciousness has somehow emerged from arrangements of matter and is capable of contemplating its own existence. Whether or not we are in a simulation, the fact that reality appears to run on deep mathematical laws, that the universe is comprehensible to creatures who evolved inside it, is itself one of the deepest mysteries of all. Before we look forward to humanity's future in space, we need to spend a moment sitting with one of the most extraordinary and disturbing concepts that modern physics has produced: the multiverse. The idea is not new, but it has gained serious scientific traction over the past few decades. The laws of physics as we understand them, the precise values of the fundamental constants, the strength of gravity, the mass of the electron, the energy density of the vacuum, appear to be fine-tuned in an almost uncanny way. Change any of them by even a tiny fraction, and the universe becomes inhospitable to complexity and life. Increase gravity slightly, and stars burn out too fast for life to evolve. Decrease it, and matter never clumps together into stars at all. Alter the charge of the electron, and chemistry as we know it becomes impossible. There are two broad explanations for this fine-tuning. Either the universe was designed, which is a theological rather than scientific claim, or there are an enormous number of universes, each with slightly different physical constants, and we necessarily find ourselves in one of the rare ones where the constants happen to allow our existence. This second explanation, the multiverse, is deeply uncomfortable for many physicists because it may be fundamentally untestable, but it emerges naturally from several well-established physical theories, including the inflationary model of the Big Bang and certain interpretations of quantum mechanics. The multiverse suggests that our observable universe, our entire observable universe, with its 2 trillion galaxies and its billions of years of history, may be just one bubble in a far larger sea of other universes, each with its own laws of physics, each forever beyond our ability to detect or communicate with. The cosmos may be not just large, but literally infinite, and the universe we know may be the tiniest of footnotes in a larger reality we can never access. Quantum mechanics, the physics of the very small, adds yet another layer of strangeness to our picture of reality. At the scale of atoms and subatomic particles, the universe does not behave the way everyday objects behave. Particles do not have definite positions until they are measured. They exist in superpositions of multiple states simultaneously, and the act of observation collapses those superpositions into definite outcomes. two particles can become entangled, such that measuring one instantly affects the state of the other, no matter how far apart they are. A phenomenon Einstein famously called spooky action at a distance, one that troubled him deeply, but that experiments have confirmed beyond any reasonable doubt. In the quantum world, probability rules rather than certainty, and the universe seems to have a fundamental randomness built into its foundation. This is not just a philosophical position, it has real-world consequences. Quantum mechanics underlies the behavior of semiconductors and gave us the transistor, the computer chip, the smartphone, and the entire digital revolution. The quantum world is not just an abstract curiosity of interest to physicists, it is the machinery running underneath everything we experience, the hidden engine of the visible world. And yet, despite how well we can use quantum mechanics to build things and make predictions, we still do not fully understand what it means. What does it mean for a particle to have no definite position? What does it mean for the universe to be fundamentally probabilistic rather than deterministic? These are questions that go all the way down to the bedrock of reality, and physicists are still arguing about the answers. The discovery of gravitational waves in 2015 opened a window onto the universe that we had never before been able to use. When two black holes or two neutron stars merge, they send ripples through the fabric of space-time itself, gravitational waves that travel outward at the speed of light, stretching and compressing space by amounts so tiny that they are almost beyond imagination. The LIGO detector, which first observed these waves, is sensitive enough to detect a change in the length of its 4-kilometer measurement arm by a distance 1/10,000th the diameter of a proton. Think about that for a moment. We built a machine so sensitive that it can detect a distortion of space smaller than the nucleus of an atom, produced by the merger of black holes more than 1 billion light-years away. The first detection, announced in February 2016, was the signal from two black holes colliding, a merger that briefly released more power than all the visible stars in the observable universe combined. And the only evidence it left in our part of the cosmos was a slight wobble in space-time, lasting less than a second. Gravitational wave astronomy is now a growing field, with detectors on multiple continents and plans for even more sensitive space-based detectors in the coming decades. Each detection tells us something new about the extreme objects populating the universe, their masses, their spins, the environments they live in. We are hearing the universe now as well as seeing it. And what we are hearing is strange and wonderful and unlike anything we expected. Let us come back to Jupiter one more time, because there is something about this giant planet that serves as a perfect metaphor for everything we have been exploring. Jupiter is the oldest planet in our solar system. New research suggests it formed within the first few million years after the Sun ignited, making it the senior member of our planetary family. It has been here, holding its place, absorbing impacts, deflecting threats, generating its enormous magnetic field, the strongest of any planet in the solar system, and presiding over the evolution of every other world, including ours, for more than 4 billion years. It has watched, in its indifferent planetary way, as our world transformed from a molten ball of rock into a thriving biosphere. It was here before the first bacteria. It was here before the first fish. It was here before the first tree, the first dinosaur, the first primate, the first human. and it will be here long after we are gone, unless something truly catastrophic reshapes the solar system in its entirety. Jupiter is a reminder that we are not the center of anything. We are not the purpose of anything. We are a brief, beautiful, perhaps unique experiment in complexity and consciousness, happening in one corner of one galaxy in a universe so vast that our entire world is by cosmic scale less significant than a single grain of sand on all the beaches of the earth. And yet, here's the thing. Here's the thing that should fill you not with despair, but with wonder, with purpose, with a sense of the extraordinary improbability of your existence. In all of that vastness, in all of those hundreds of billions of galaxies, each containing hundreds of billions of stars, across all of that incomprehensible scale and age and depth, in all of that, as far as we know, only here, on this one small rock orbiting an ordinary star in the outer arm of a spiral galaxy, has the universe become aware of itself. Only here has matter arranged itself in such a way that it can look back at the cosmos and ask questions about it. Only here, maybe only here, has the universe produced beings capable of love, music, art, mathematics, philosophy, grief, joy, and the aching desire to understand where we come from and where we are going. Carl Sagan said it in a way that has never been improved upon. We are a way for the universe to know itself. That is not a poetic flourish. That is, in the most literal sense, what consciousness is. It is the universe reflecting on its own existence through the medium of living things. You are the cosmos looking at itself in a mirror, confused by its own beauty, terrified by its own scale, and relentlessly curious about everything beyond the edge of what it can see. The mysteries we have explored in this journey, Jupiter's ancient storms, the birth of the universe, the nature of black holes, the silence of the cosmos, the acceleration driven by dark energy, the possibility of life elsewhere, the warping of time near massive objects, the future of our species among the stars. These are not problems waiting to be solved and forgotten. They are invitations. They are the universe extending its hand and asking you to pay attention, to engage, to think harder and look deeper, and stay curious no matter how comfortable or distracted your daily life might tempt you to be. Every generation thinks it stands at the edge of human knowledge, and every generation is surprised by what the next generation finds. The scientists working today did not predict the discovery that the universe's expansion is accelerating. They did not predict how complex and ancient the galaxy's center would turn out to be. They did not predict the sheer variety of exoplanets that the Kepler Space Telescope would reveal in its first few years of operation. Thousands of planets around other stars, many of them potentially the right size and temperature to host liquid water on their surfaces. Every time we build a better instrument, every time we look a little harder or think a little differently, the universe surprises us. And that in itself is one of the most beautiful facts of all. The next few decades may be the most consequential in the history of our species and our understanding of the cosmos. We are on the verge of sending humans to Mars. We are developing new generations of space telescopes that will be able to study the atmospheres of exoplanets in detail, looking for the chemical signatures of life, oxygen, methane, water vapor, in the air of worlds orbiting distant stars. We are sending missions to the outer solar system to study the ocean moons that may harbor life in our own cosmic neighborhood. We are building gravitational wave detectors of increasing sensitivity that can hear the ripples in space-time created by merging black holes and neutron stars, opening an entirely new way of listening to the universe, a way that does not depend on light at all. We are even beginning to ask, seriously and scientifically, whether faster than light travel might one day be possible through the warping of space-time, not in violation of Einstein's laws, but in creative application of them. Ideas like the Alcubierre drive, which remains deeply theoretical, but which does not immediately break any known laws of physics. We are a species at the very beginning of a journey that may ultimately take us to the stars. And the fact that we are alive right now, in this moment of acceleration and discovery, is not something to take for granted. Before we fully close this chapter of our journey through the cosmos, we need to spend a moment with one of the most extreme objects in the universe that often gets overshadowed by the drama of black holes. Neutron stars are the collapsed cores of massive stars that have exploded in supernovae, but were not quite massive enough to collapse all the way into black holes. What remains after the explosion is a sphere of pure neutrons, typically only about 20 kilometers across, roughly the size of a city, but containing more mass than our entire sun. A single teaspoon of neutron star material would weigh about 10 million tons on Earth. The gravity at the surface of a neutron star is about 200 billion times stronger than Earth's. If you fell toward a neutron star from a height of just 1 meter above its surface, by the time you hit, you would be traveling at about 2 million kilometers per hour. Some neutron stars spin hundreds of times per second, emitting beams of radio waves from their magnetic poles with such regularity that when they were first discovered in 1967, astronomers briefly thought they might be signals from an alien civilization. They named the first one LGM-1 for Little Green Men before the physical explanation became clear. These objects are called pulsars, and they are nature's most precise clocks, some of them ticking with regularity that rivals the best atomic clocks we have built. When two neutron stars spiral toward each other and collide, they produce not just gravitational waves, but an explosion called a kilonova. And kilonovae are where gold comes from. All the gold on Earth, every ring and coin and trophy, was forged in the collision of neutron stars that died long before our solar system was born. Wearing gold is, in the most literal possible sense, wearing the remnants of a cataclysm that happened before our world even existed. Consider for a moment the speed at which our understanding of the universe has accelerated over just the past 100 years. In 1900, we did not know other galaxies existed. The Milky Way was thought to be the entire universe. In 1924, Edwin Hubble proved that the fuzzy objects we called nebulae were in fact entire separate galaxies, billions of light years away, and the universe expanded in our minds overnight from a single galaxy to something unimaginably larger. In 1929, Hubble showed that those galaxies were moving away from us, and the universe was expanding. In 1965, the cosmic microwave background was discovered, the faint afterglow of the Big Bang itself, still permeating every direction of space, a photograph of the universe when it was just 380,000 years old. In 1998, the accelerating expansion of the universe was discovered, rewriting our understanding of what the future holds. In 2012, the Higgs boson was confirmed at the Large Hadron Collider. In 2015, gravitational waves were detected. In 2019, the first image of a black hole's event horizon was captured by the Event Horizon Telescope, a global network of radio telescopes working together as one Earth-sized instrument. Each of these discoveries was, at the time of its announcement, one of the most significant events in human intellectual history. And they are accelerating. The next 100 years may contain discoveries that make all of the above look like preliminaries. We are not at the end of the story. We are barely past the first page. Think about what it would mean to be the generation that confirms life exists beyond the Earth. Think about what it would mean to be the generation that first steps foot on another planet. Think about what it would mean to be alive when a signal arrives from a distant star, unmistakably artificial, unmistakably intelligent, proof that we are not alone in a universe we once feared was empty. These events may not happen in your lifetime, but they might. The pace of discovery is not linear, it is exponential. And the universe, for all its mystery, for all its silence, for all its incomprehensible scale, has already given us one extraordinary gift. It has made us curious. It has built into us, somewhere in the deep architecture of our minds, a hunger to know, an inability to simply accept the world as it appears without asking what lies beneath it, what came before it, what might be beyond it. That curiosity is not a bug in our design. It is the most important feature we have. It is the reason we built telescopes and sent probes to the edge of the solar system and pressed our ears against the silence of the cosmos, hoping to hear something call back. We started this journey with a storm on Jupiter, a tempest that has been raging for 3.5 centuries, a force of nature so persistent it makes all of human history look like a long weekend. But that storm, impressive as it is just one detail on one planet in one solar system in one galaxy among trillions. The universe is not waiting for our understanding. It does not need our recognition to exist. The black holes are consuming matter, whether or not we know about them. The dark matter is holding galaxies together, whether or not we can detect it. The distant galaxies are racing away from us, whether or not we find it unsettling. The cosmos does not care about our comfort or our confusion. But it has, through a chain of events spanning almost 14 billion years, created beings who care about it. And that, perhaps more than anything else, is the deepest mystery of all. Not just what the universe is made of, or how it began, or how it will end, but why any of it should be experienced, understood, or wondered at by creatures like us on a small blue rock, circling an ordinary star in the vast and silent dark. So next time you look up at that bright, steady light in the night sky, the one that is Jupiter, the giant that guards our corner of the cosmos, let yourself feel small for a moment. Not diminished, not frightened. Small in the way that standing at the edge of the ocean makes you feel small. Small in a way that reminds you that you are part of something incomprehensibly large and old and beautiful. Small in a way that makes the life you have, the consciousness you carry, the few decades you spend aware and alive on this planet, feel not insignificant, but miraculous. Because in a universe of trillions of galaxies and incomprehensible emptiness and ancient darkness, you are here. You are awake. You are asking the questions. And that, in the end, is everything. The universe does not owe us understanding. It did not arrange itself to be comprehensible. The laws of physics did not have to be mathematical, did not have to be consistent, did not have to be learnable by creatures who evolved to find fruit and avoid predators on a small savanna in Africa. And yet here we are, reading the equations written in the structure of space and time, hearing the music of black hole collisions in the vibrations of mirrors, seeing galaxies that formed before our planet existed in the light that finally reached our telescopes after billions of years of travel. We did not build our brains to do this. We built our brains to survive. And somehow, against all reasonable expectation, it turns out that the same minds capable of tracking game and solving social problems are also capable of quantum field theory and general relativity and the detection of gravitational waves. The universe gave us more than we needed. It gave us the ability to be curious about everything, including itself. Use that ability. Look up. Ask questions. Stay humble. Keep going. The universe is patient, and it has been keeping its secrets for almost 14 billion years, but it has never stopped leaving clues for anyone paying enough attention to find them. There is one more thing worth saying before we close. One final idea that ties everything together into a single thread of meaning. Every civilization that has ever existed on this planet, every empire and culture and tribe and nation has looked up at the same stars. Different names, different mythologies, different frameworks for understanding what they saw, but the same stars, the same Jupiter, the same band of the Milky Way, the same cold, silent, and immovable backdrop of the cosmos. For most of human history, we looked at that sky and saw gods and patterns and signs and portents. We saw a ceiling, not an opening. We saw decoration, not depth. And then, gradually, over a few extraordinary centuries, we began to understand what we were actually looking at. And the reality turned out to be so much stranger and grander and more beautiful than any mythology ever devised. The truth is that you are standing on a planet that formed from the debris of dead stars, orbiting a star that will one day expand and engulf it, in a galaxy that is slowly being pulled toward a collision with its neighbor, in a universe that is flying apart at an accelerating rate, sustained by forces and substances we cannot see or fully explain, perhaps one of countless universes in a multiverse beyond our ability to detect, temporarily inhabited by creatures made of atoms that have been around since the first few minutes after the Big Bang, now capable for the first time of understanding something, anything, about what all of this is and how it works. That is not a reason to despair. That is the greatest story ever told, and you are in it. Stop whatever you are doing right now. Just stop for a second and think about this. You are sitting on a rock. That rock is spinning at roughly 1,000 miles per hour while simultaneously hurtling through space at 67,000 miles per hour around a star that is so enormous it could swallow more than 1,000,000 Earths. That star, the one we call our sun, the thing that warms your face on a summer afternoon and grows our food and makes life possible, that star is just one of 200 billion stars in our galaxy alone. And our galaxy is just one of at least 2 trillion galaxies in the observable universe. 2 trillion. Say that number out loud. Let it sit in your mind for a moment. 2 trillion entire galaxies, each containing hundreds of billions of stars, each of those stars potentially surrounded by worlds. And we are here, on this one tiny rock, looking up at the night sky, wondering what is out there. This is not a documentary about facts and figures. This is a journey, and once you take it, you will never look up at the night sky the same way again. Let us start close to home, because even in our own cosmic backyard, there are things so staggering, so overwhelming, that most people have never truly grasped them. Right now, if you could look up on a clear night, you might see a bright object in the sky that is not a star. It does not twinkle the way stars do. It holds a steady, almost intimidating glow. That object is Jupiter, the largest planet in our solar system, a world so massive that it could fit all the other planets inside it with room to spare. We have known about Jupiter for thousands of years. Ancient astronomers tracked its movement across the sky. Galileo pointed his primitive telescope at it in 1610 and saw 4 small moons circling it, which was the first evidence in history that not everything in the universe revolved around the Earth. But even today, with all of our technology and spacecraft and scientific knowledge, Jupiter remains one of the most mysterious, dramatic, and terrifying objects in the cosmos. And understanding Jupiter is the first step to understanding something far, far larger.